Hello and welcome everyone to our webinar that's offered jointly by the Mobilize Center and Restore Centers at Stanford University. My name is Matt Petrucci. I'm the Scientific Program Manager of both these centers, and I'm excited to serve as your moderator today. Today's speaker is Gurchiek, who will be discussing his recent work that addresses our gap in understanding of hamstring injuries using a unique and more realistic data set compared with previous studies. He will present his analyses and findings and will also explore the effects of hip-knee coordination on hamstring lengthening during running. Dr. Gurchiek will also discuss the potential practical impacts of these findings, including the use of OpenCap for informing coaching practices and movement screening of athletes. Today's webinar is brought to you by the Mobilize Center and Restore Centers, which are both supported by the National Institutes of Health. The Mobilize Center is focused on developing and disseminating state-of-the-art biomechanics and machine learning tools for researchers to analyze human movement. The Restore Center is working to make these and other tools for real-world assessment of movement more widely available to the rehab research community. Now, before we get started, a couple of quick reminders about the format of the webinar. We will only have a research talk and no tutorial this time, so we'll take your questions once at the end of the research talk. Please type your questions into the Q&A panel in Zoom, so not the chat, the Q&A panel, and we'll review them from there. One other thing to note is this webinar will be recorded and posted to our YouTube channels. All right, now I'd like to introduce our speaker for today. It's Dr. Reid Gurchiek is an assistant professor in the Department of Bioengineering at Clemson University, where he directs the Human Movement Biomechanics Lab. His research combines mobile and wearable technologies with musculoskeletal modeling and simulation for biomechanical analysis. His lab applies these tools for musculoskeletal rehabilitation and aging science. He trained with Professor Scott Delp at Stanford University as a WUSI Human Performance Alliance postdoctoral fellow, and with Professor Ryan McGinnis at the University of Vermont, where he obtained his PhD in mechanical engineering. With that, we're excited to have you all here today. I know we're all excited to hear Reid speak about his research, so I will let him go ahead and begin.
Thanks, Matt. Matt, can you confirm that you're seeing that? Matt, are you seeing my talk here?
Yep, looks good.
All right, thanks. Well, thanks for the intro. And like Matt said, today I'll be presenting some of the work during my time as a postdoctoral fellow in Dr. Scott Delp's lab there at Stanford University, investigating hamstring kinematics during accelerative versus constant speed running. Hamstring strain injuries are a big problem for many athletes. HSI there is an abbreviation for hamstring strain injury that'll be used throughout the talk. These injuries have been found to be the #1 time loss injury in several sports, including soccer and track and field, and with relatively high re-injury rates. There was one review paper that found across 5 studies an average of about 30%, but as high as 63%. So prevention is really important in this space. I want to give you an idea for how the injury typically presents. The biceps femoris appears to be injured more often than the medial hamstrings. Injury usually occurs at the muscle tendon junction, and they typically occur during dynamic running activity. And there's debate about exactly when during the running cycle the injury happens. Most people think it's somewhere at the end of swing phase, just before the foot hits the ground, or in early stance phase after it's hit the ground. They're usually non-contact injuries, and often in the literature, they're viewed as an overuse injury resulting from the accumulation of muscle tendon damage over time. They occur more often in games than in practices, and usually later in the game rather than earlier. And it's for this reason that there's been an interest in investigating the potential influence of fatigue on injury risk. And I should note, there's some recent evidence that the incidence rate of the injuries occurring during practice or training sessions is increasing in some sports. Now, if you're familiar with the space, you know that there's been a lot of research done in this area, but it is still ripe for discovery and innovation. For example, there's some evidence that this problem is a growing one. A research group has been tracking these injuries in the UEFA Professional Soccer League since 2001. And they reported that in 2021, hamstring injuries constituted 24% of all injuries, and that was double the proportion that was observed in the first season that they started tracking, 12% in 2001. So to reverse this course, research efforts aim to understand how do we identify athletes that are at risk? Once we do, what exercises should we prescribe? How do we program load? What should we train for to prevent injury? How do we rehab an athlete following an injury? What should the return to play criteria be? And how do we monitor load? In terms of load monitoring, both to understand who might be at risk due to overuse, but also due to underloading. There's a potential that people could be without sufficient stimulus to promote favorable adaptation. Now, interestingly, there was a different study published by Barnes et al. In 2014 that observed a change in the exposure to sprinting and dynamic activity of professional soccer players during gameplay. And it was within this time interval indicated by the red curly bracket in the figure. They tracked over 1,000 players for 7 seasons in the English Premier League from 2006 to 2013, and they describe an evolution in the technical performance of soccer players. Again, notice that their monitoring is within this interval in which the proportion of hamstring injuries doubled. And so during this time frame, they observed a 2% increase in total running distance. But there was evidence that this running activity was more and more characterized by high speeds and being dynamic in nature. There was a 35% increase in the total sprint distance, an 85% increase in the number of sprints, and the proportion of those sprints, which were called explosive in nature, increased from 34 to 47%. And to designate it as explosive was based on how quickly the athlete entered the high-speed zone. So keep this in mind as we go forward, because it was findings like this and others which motivated our interest in accelerative running. We know that high-speed running can present injurious circumstances. During high-speed running, the hamstrings are stretched to long lengths. They're stretched quickly and under very high loads as they arrest the motion of the shank as it rapidly swings forward. The net result is that the hamstrings do large amounts of eccentric work during high-speed running, and previous studies have shown that eccentric work, negative work of the muscle tendon unit, is a strong predictor of microdamage within muscle. Much of what we know about hamstring mechanics during running has come from treadmill running experiments. So in these controlled laboratory experiments, we've learned a lot about the large forces that are present in the hamstrings, their pattern of loading, at what time during the gait cycle loading peaks, and then coupling empirical data with modeling and simulation has enabled characterization of the loading that is imposed on the hamstrings during running. This is one advantage of musculoskeletal modeling and simulation, is that it permits the estimation of variables that can't be measured non-invasively or easily, like, for example, the length of the hamstring during running or the muscle tendon unit force. Moreover, speed being controlled for enables investigations of the effects of different speeds, maximal and submaximal running speeds. Daryl Thelen in particular made important contributions to this research in the early 2000s, and many others have made great contributions since then. However, it's difficult to study accelerative running on a treadmill, and recent data suggests hamstring injuries often do occur during acceleration. This is a paper that was published recently in 2022 in the British Journal of Sports Medicine. They retrospectively analyzed videos of hamstring injuries in professional rugby players, and across 2 seasons and 51 observed hamstring injuries, 17 videos of those injuries met the criteria to be analyzed. Some of the injuries occurred during kicking, some during tackling, but most of them occurred during running activity. And interestingly, all the occurrences during running activity were described as being accelerative in nature. That is, the athletes were accelerating from a submaximal speed rather than having been running at top speed. Now, this study played an important role in motivating ours, but there was another paper published in 2023 which told a similar story. This too was a retrospective analysis of videos during which hamstring injuries were captured. This followed a Serie A football club for 3 seasons. And they were able to analyze 34 non-contact time loss injuries out of a total of 68. Most of them, that is 50%, were hamstring injuries. 88% of all of these hamstring injuries occurred during running activity, and 12% of those were during acceleration at submaximal speeds. So hamstring injuries sometimes occur when an athlete is accelerating from a submaximal speed. And we were interested in the hamstring mechanics during accelerative running. And specifically, we sought in this study to answer the following two research questions. First, what is the relationship between running speed and hamstring kinematics during accelerative running? And secondly, how do hamstring kinematics compare during speed-matched accelerative running versus constant speed running? By hamstring kinematics, I just mean the length of the hamstring and how fast it lengthens, that is, its lengthening velocity. To answer these research questions, we set up the following experimental protocol. We had 10 athletes, 5 men and 5 women, run over a running surface in their own running shoes in an out-of-lab environment. We set up 2 iPhones on tripods to video the participants as they ran under 2 conditions. One was a constant speed condition, and the other was accelerative running. We wanted to investigate the effect of running speed, so we had them run at 6 different speeds. 2 were done at self-selected speeds. One was a jogging pace, and the other was a more brisk, faster running speed. It was more than a jog, but it was still submaximal, and it was self-selected. And then 4 were done at prescribed speeds, 3, 4, 5, and 6 meters per second. So we had a total of 6 trials for both accelerative and constant speed running. For the prescribed speed trials, we would set up cones along the running lane, like shown in the figure here, with either 5 or 2.5 meter spacing. And we set a metronome to beep at a frequency such that the athletes pass the cone at the prescribed speed. For each of these speeds, the athletes were given time to practice and as much time as they needed to fully recover to avoid fatigue. It wasn't imperative that they match the speed exactly, but rather that we captured a range of speeds so we could analyze its effect in a regression analysis. For each trial, participants began 35 meters away from the center of the capture volume. And so for the constant speed trials, they would simply run past the cameras at the set speed, like shown here. For the accelerative trials, they would first begin running at the same speed as for the constant speed trials, but then they were given an unanticipated auditory cue to accelerate as fast as possible once they were within the capture volume. So that looks something like this. This is sometimes called a flying sprint, and we implemented this to better represent in-game accelerative running activity, which rarely starts from a still start, like a 3-point stance and a 100-meter sprint. Rather, usually athletes will already have been moving when they begin to accelerate, for example, at a submaximal speed. Shown here are still frames from the videos of the 2 cameras in both a constant speed trial on the left and an accelerative running trial on the right. And this is to give you a sense of the field of view of the cameras. We used OpenCap to automate the recording, synchronization, and processing of the video data. And I'll refer you to the original publication for more details on how OpenCap works. But briefly, it first uses an open source pose detector to identify 2-dimensional key points, for example, joint centers, in each camera's field of view. Then the 3-dimensional position of each key point is determined using triangulation, and that's based off a calibration step that precedes the data collection. A neural network is then used to determine a dense set of markers, the 3D positions of a dense set of markers, similar to what's typical in a traditional motion capture lab. And then an inverse kinematics algorithm is run to calculate the joint angles. We used a 3D musculoskeletal model that was calibrated to the person's weight and their body segment dimensions, and that was determined from a static pose as a part of the routine OpenCap data collection procedures. We analyzed the 3 steps that were closest to the center of the capture volume for each constant speed trial. And for the accelerative running trials, we analyzed the first 2 steps that immediately followed the initiation of the acceleration. And this was to ensure that we captured the first full stride once they began to accelerate. So that's 2 steps for each accelerative trial and 3 for each constant speed trial. We analyzed only the swing leg during each step. So for example, for a step as depicted in the figure, we would analyze only the hamstring kinematics of the right leg, which starts at the foot contact of the left leg and ends with the foot contact of the right leg. We used negative going, 0 crossings in the shank sagittal angular velocity signal to estimate foot contact events. This event is common for this purpose in inertial motion capture, as it follows a relatively large magnitude positive signal, like you can see in the figure, and that's associated with the swing phase, and thus it's reliably identified algorithmically, and it facilitates a consistent step segmentation. We verified the foot contacts manually through visual inspection of each video, and we confirmed that the entire lengthening phase of the hamstrings was being captured by this segmentation algorithm. To calculate the hamstring NTU kinematics, we first low-pass filtered the coordinate data at 15 Hertz, and that was based off a residual analysis where we determined that 90% of the signal power was contained below that cutoff frequency. We used OpenSim to calculate the peak biceps femoris length during the step and the lengthening velocity. The lengthening velocity is calculated from the time derivatives of the hip and knee joint angles. So for example, the subscript KF here indicates the knee flexion degree of freedom, and HF denotes the hip flexion degree of freedom. Now, MTU velocity is calculated as the following sum of products. Each joint angle speed is multiplied by the moment arm, which is denoted by R, of the MTU about that joint angle for that degree of freedom. Now, because running is primarily a sagittal plane activity, knee flexion and hip flexion are the primary contributors shown here in red and blue. But we also took into account the effect of hip adduction and rotation motions on the MTU kinematics. I promise this is the only math, but I show you this just because we did an analysis of the relative contributions from the hip and the knee to the hamstring lengthening velocity, and this demonstrates how we did it. In our primary analysis, we considered the average lengthening velocity. That is the sample average of all the strictly positive MTU velocities, as opposed to the peak MTU velocity. And this is because we found this to be a more appropriate surrogate for the more relevant kinetic variable, which is eccentric work, and because it's less susceptible to noise from numerical differentiation. Nonetheless, we did also characterize and perform a post hoc regression analysis with peak lengthening velocity as the outcome. To account for variation in height across our participants, we normalized all the MTU lengths and the lengthening velocities by the MTU length during a standing posture called the neutral length. So all the MTU length data that I'll report in this talk and in the paper are given in neutral lengths, and the lengthening velocity data are reported in units neutral lengths per second. Finally, we calculated the running speed for each step by dividing the step length by the step time, and running speeds were normalized by the person-specific top speed, which was obtained in a maximal effort 30-meter sprint. We manually reviewed the quality of the kinematic reconstructions for each running trial from each participant. Occasionally, the reconstruction will fail, and it's manifestly obvious upon visual inspection when this happens. We also removed outliers, defined as a value 3 standard deviations or more away from the mean. And those statistics were based on both discrete outcomes like peak length and lengthening velocity, as well as several relevant time series outliers. So based on this criteria, we removed about 20% of the total possible steps, and that left us with 140 steps during constant speed running and 99 steps during accelerative running available for analysis. We performed 2 separate linear mixed effects regression analyses, one for each of the primary outcomes, peak length and average lengthening velocity. These primary outcomes were the dependent variable, and speed was the independent variable, along with the running condition, accelerative or constant speed, as a categorical variable. And we modeled a random effect of person, both for slope and intercept. All right, so let's look at the results. Shown here are the kinematic trajectories for the biceps femoris MTU length in the top row, the hip flexion angle in the middle row, and the knee flexion angle on the bottom row. Each column of figures is for a different range of running speeds. The slowest speeds are on the left, the far left being below 55% of top speed, and the fastest speeds on the right. The far right has speeds between 85 and 100% of top speed. The teal color is for constant speed running, and red is for accelerative, and that'll be the case for the remainder of the talk. And the x-axis is the percentage of the step cycle. And this data shows that the motions of the hip and the knee and the related effects on hamstring length are generally similar. There's a similar kinematic pattern between the two conditions, right? You've got the hamstrings are stretched up to some peak length, and then there's a brief shortening period just before contact. And a similar pattern is observed across the faster running speeds. In fact, the two trajectories for the accelerative and constant speed conditions nearly coincide at the fastest speeds. And a similar general trend was observed for the hip and knee trajectories as well. Now, it's not surprising that they're more similar for faster running speeds, right? A person is less able to accelerate the closer they are to their top speed, and thus one would expect the kinematics to converge there. However, the differences become more and more pronounced for slower speeds. In the leftmost column, for the slowest running speeds, the two conditions appear to diverge the most about halfway through the step cycle, right here. And so they're most different during late swing phase, just before the foot hits the ground. And notice that this is when the hamstring lengths peak, as seen in the top right or in the top left figure. So let's look at that more closely. By comparing the peak lengths directly, we found that the hamstrings are stretched more during acceleration than in constant speed running, and especially at slower running speeds. So each data point in this scatter plot represents the peak MTU length during a step for a single person and a single trial. Again, red colors for accelerative running and teal for constant speed. The solid lines are the results of the linear mixed effects regression analysis, and the shaded area represents the 90% prediction interval. It's evident from our analysis that peak MTU length increases with running speed, and that's true for both running conditions. Running speed is shown on the x-axis here, again being normalized by the top running speed, so a value of 1 is top running speed. As for the visual inspection of those time series on the previous slide, the running conditions converge to the same value at top speed, where the hamstrings are stretched up to about 11 or 12% of their length in the neutral pose. However, the slopes of these two lines were significantly different, indicating that for slower running speeds, the peak hamstring length is more and more greater in accelerative running than in constant speed running. And based on the overlap of the shaded area, the 90% prediction intervals, that difference becomes significant, close to 75% of top speed. Now, practically, this means that running speed alone may be insufficient for characterizing exposure to high-risk circumstances like long lengths. Rather, our data suggests that the accelerative nature of running should be considered in those applications. For example, imagine a situation where wearable GPS units are used to monitor exposure to high running speeds, and high running speed may be used as a surrogate measure to indicate that the hamstrings may be exposed to long lengths. Our data, to some extent, supports this, right? As running speed increases, so also does the peak hamstring length. But imagine that the observed running speed is, for example, 50% of top speed. If the accelerative nature of the running task is neglected, peak hamstring length may be underestimated. Our regression analysis suggests that the peak hamstring length when accelerating from only 50% of top speed could be equivalent to that observed during constant speed running at 88% of top speed. We made a similar conclusion based on how fast the hamstrings are stretched. This plot is nearly the same as the one before, except this time on the y-axis is the average lengthening velocity per step. As for the analysis of peak lengths, again, we found that the slopes of these two lines were significantly different and converged toward a similar value at top speed, suggesting that the hamstrings were stretched faster during accelerative running and especially when accelerating from slower speeds. So the hamstrings are stretched more and faster during accelerative than constant speed running. And we were curious why. The hamstrings can be lengthened due to hip flexion and or knee extension. So opposite actions using that familiar terminology. And likewise, hip extension and knee flexion act to shorten the hamstrings. Thus, if the hip and the knee have similar actions using this terminology, for example, if they extend together, as shown in this figure on the right, the MTU length would have less of a tendency to change. The contraction would be more isometric in nature. Now, if the hip and the knee extension rates are exactly the same, the MTU motion would still have a non-zero velocity. It won't be exactly an isometric contraction, and this is due to differences in the moment arms of the hamstring MTU about the hip and the knee, as we'll see. But the idea is that the shortening action of hip extension cancels out the lengthening action of knee extension. And interestingly, this is more akin to what's observed in actual running. It's not perfect, but hip knee action is more or less in phase. For example, the hip and the knee extend together in late swing phase as the foot is being driven down toward the ground. And in early swing phase, they more or less flex together as the knee is being driven forward. And this is evident in those time series figures that were shown previously. Notice that the hip and the knee flex together up to about 50% of the step cycle. The knee then begins to extend relatively quickly, while hip flexion transitions to an extension action more slowly, and it's realized only slightly later. Notice that although the knee and the hip flex together in the beginning, the hamstring length in that top figure does not remain constant. Rather, it lengthens. And this is due to both differences in how quickly the hip and the knee are rotating, and because of differences in the moment arm of the biceps femoris being larger about the hip flexion degree of freedom than knee flexion. Thus, the lengthening action of hip flexion appears to win out over the shortening action of knee flexion. Now, this highlights the importance of hip-knee coordination. If the knee does not flex with the hip in early swing phase, then the hamstrings would be stretched even faster, as there would be less of a countering action from the knee to oppose the lengthening action of the flexing hip. Similarly, notice that during accelerative running, the hip flexes more, right? You've got the red line above the teal line in this middle figure. And you'll notice that simultaneously in the knee flexion figure on the bottom, the knee extension is delayed and it's slower. The slopes of the red line is less steep than the teal line. And the net effect is that the hamstrings are stretched less than they would have been if the knee motion weren't coordinated with the hip in this way. And this is consistent with other research that suggests a potential influence of altered coordination on injury risk. Now, to augment this visual analysis, we performed additional linear mixed effects regression analyses to investigate the relative influence of hip and knee motions quantitatively. Again, we found that the differences were driven primarily by differences in the hip motion. Here we're looking at how much of the average lengthening velocity is due to hip motion on the left and how much is due to knee motion on the right. In the left figure, you see that the MTU lengthening velocity due to the hip motion is greater than in accelerative running than in constant speed running. The red line is above the teal. In contrast, the MTU stretch rate from the knee motion in the right figure is less in accelerative running than in constant speed running. And this is explained by the phenomenon described on the previous slide. The lesser contribution of the knee motion to MTU lengthening velocity in accelerative running is due to that delayed extension action compared to constant speed running. Now, again, you'll recall that the net result was still a greater lengthening velocity in accelerative running. Thus, we conclude that the hip motion is driving the differences between the two running conditions. We also looked at the hip and the knee angles at the instant that the MTU reached its peak length. The hip flexion angle is shown on the left, knee flexion angle on the right. So looking at the hip flexion angles on the left, we see that the hip is configured similarly at the instant of peak MTU length, regardless of the running speed. The slope of the red line in the left figure is relatively flat. And this is a much different story than for constant speed running, where the hip range of motion is much less at slower running speeds and increases with running speed. And yet, if you recall, the peak MTU length was running speed dependent. It increased with running speed. So why weren't the peak MTU lengths also independent of speed, showing a nearly flat trajectory as for the red line in the figure on the left here? It's because of the knee. So if you look at the figure on the right, we observed a negative slope for the knee flexion angle at the instant of peak MTU length with respect to speed. So as people accelerate from faster speeds, the MTU length peaks in a more extended knee position, or equivalently, as depicted in the figure, a less flexed knee position. I was kind of surprised by the flat line of the hip angles on the left for the accelerative condition and was curious whether the roughly 70 degrees of hip flexion was the result of a more anteriorly tilted pelvis, for example, that might be expected if someone is leaning forward more in acceleration, or from a more rotated thigh in the sagittal plane. And that analysis is shown here. We found that it was a little bit of both, but mostly a more sagittally rotated thigh. Specifically, we found that about a third of the hip flexion at peak MTU length was due to pelvis tilt, and that's being shown on the left, while about 2/3 was due to thigh tilt, again shown on the right. These figures here depict the results of a linear mixed effects regression analysis, as for the others shown on previous slides. So the main takeaway is pretty well captured by the title of our paper. The hamstrings are stretched more and faster in speed-matched accelerative running compared to constant speed running. Secondly, the differences are more pronounced during slower speed running, and we think this may have implications for athlete monitoring applications, as discussed before. And finally, our results support prior work that suggests the importance of hip-knee coordination on hamstring kinematics during running and the potential influence on injury risk. We describe several limitations in the paper, including the lack of a kinetic analysis. This includes both joint level kinetics, like joint moment or joint power, as well as muscle level analysis, like MTU force or work. And this should be done in future work. We had a relatively small sample, and while everyone included in our study did regularly participate in field-based sports that require sprinting, not all of them specialized in sprinting specifically. Our analysis only considered a step cycle, which we confirmed was sufficient to capture the lengthening action of the hamstrings, but we did not consider hamstring mechanics during stance phase, and there may be differences between accelerative and constant speed running in stance phase as well. Finally, while OpenCap has not been validated specifically for flying sprints, it has been validated for dynamic motions like running and drop jumps. And we found OpenCap to have been a strength of the study, as it facilitated this unique experimental approach involving a running task that required a relatively large space, and we could not have done it inside the Human Performance Lab at Stanford. Moreover, we implemented a careful procedure for verifying data quality, and we confirmed that our results were consistent with prior work where we could make such comparisons. The paper describes several. I'm showing 3 examples here. So for example, concerning the peak MTU length in top speed running, one study reported between 9 and 11% MTU strain, another reported 12%, and this is comparable to the value that we calculated, which is about 11%. Shash et al. In 2013 reported the peak MTU lengthening velocity during top speed running to be about 2.2 neutral lengths per second, and this is the same value calculated from our data. And then finally, the range of pelvis tilt angles based on our regression analysis for both running conditions at top speed was between 14 and 19 degrees, and this is comparable to what's been reported in other studies. Another limitation is that our accelerative running task was strictly positive acceleration, where speed was increased. However, the same studies that motivated our investigation of accelerative running also reported that some injuries occurred during deceleration. And there have been some studies that explore the kinematics and kinetics of decelerative running, but I've not seen any analysis of the hamstring mechanics specifically as done in this study. And we've started to investigate this ourselves here at Clemson. This is a study being led by Andrew Polson, who's a bioengineering undergraduate student here, along with another student, Ryan Coulin. In this study, we have athletes run as fast as possible to a cone, at which they must come to a stop and then backpedal. And we position the cameras to capture the deceleration that's required of that task, as shown in this video. We haven't finished data collection, but we've begun to preliminarily analyze some of our data. The top figure here shows the running speed during that deceleration task. You see a peak running speed is reached before a sharp deceleration. They come to a stop where it passes the zero velocity, and then they backpedal, indicated by a negative running speed. The bottom figure shows the hamstring lengths normalized by the neutral length. So you've got the right leg in red and the left leg in blue. And this figure in the bottom depicts a general trend that we're starting to observe, where the range of hamstring lengths for each subsequent step during deceleration become less and less, but the ceiling remains relatively unchanged, and it peaks around 11% strain, which you'll recall is what was observed for top speed, constant speed running in our accelerative versus constant speed study. So we hope to finish data collection and explore this more thoroughly in the coming months. Finally, I want to close by revisiting practical application and more broadly concerning the use of OpenCap to facilitate movement screens at scale. Last year, we received some pilot funding to assess the feasibility of incorporating movement assessments into the annual physical examinations of athletes here at Clemson. The idea is that in addition to blood work and baseline concussion testing, strength testing, and so on, we would evaluate movement in a movement assessment station using the OpenCap system. And if someone is injured during the season, we now have pre-injury movement data that can be used as a reference for comparison, for example, to evaluate progression during rehabilitation. In our efforts to establish this operation just for preliminarily assessing feasibility, we opted for a most basic movement assessment. It involved only walking and squatting. So across 8 days over the summer last year, and with a relatively small team of undergraduates, we tested 119 athletes across several sports: men's and women's soccer, women's lacrosse, softball, baseball, track and field, and a handful of football athletes. We're planning on expanding our assessment this year to include a flying sprint, similar to the task that was described earlier to represent accelerative running in our study. And we intend to explore the utility of movement-based injury risk factors for predicting injury in a prospective design. All right, with that, I'll say thanks for listening, and I want to recognize my collaborators, Zachary Teplin, who helped tremendously with this study in an undergraduate summer research program. He handled most of the data collection along with the help of Julie Muccini. And then the other co-authors on the paper, Antoine Felice, Jennifer Hicks, and Scott Delp. And again, this work was supported by the WUSI Human Performance Alliance, the Mobilize and Restore Centers, and our ongoing efforts here at Clemson are supported by the Clemson Creative Inquiry Program and SC TrimH. Thanks.
Great. Thank you so much, Reed, for the super clear talk. We'll go ahead and start the Q&A. So again, if you have any questions, go ahead and type those into the Q&A panel and not the chat, and we'll get to as many questions as we can. The first question comes from Sam Hamner. Did hamstring kinematics include a compliant tendon to examine fiber lengths, or was it the length of the complete muscle tendon unit?
Yeah, good question. It was for the complete muscle tendon unit.
Next is from Jasper Verhoel. Why was MTU length derived from joint angles rather than the length of the hamstring muscle in the model directly?
I think both of those statements are true. Um, we calculated it from the model. The model describes how the geometry of the hamstring muscle changes as a function of the joint angles. And so it is calculated based on how the model models the kinematics of the joints and the geometry of the hamstring. And those are based on the hamstring length will change as a function of the hip and knee configurations, and that's captured by the way that OpenSim models the geometry.
Definitely. Next question is from Malehe Fakar. Can you clarify the gait event detection for foot contact? Specifically, why didn't you consider the swing phase as the toe off to the foot contact of the same limb?
Yeah, so for example, to go from foot off to foot off, I'm not convinced that we would have captured the full lengthening phase. Really, that's what was our greatest desire, was to capture peak length, peak lengthening velocity, and average lengthening velocity. And to do that, you need to have the entire time where it's lengthening. And if you recall looking at those trajectories of the hamstring length, you actually had a little valley and then a peak. And so the full lengthening phase was being captured. I'm not convinced that we would have had that from foot off to foot off. The reason why we used the event detection algorithm that we did is because it's been used in other places. Like I said, in the inertial motion capture space using gyroscopes, for example. And the shank angular velocity signal is really clean for this purpose. It's almost exclusively negative angular velocity, as the shank does mostly rotation in the direction that you're walking during stance phase. And then the shank rotates the opposite direction, which is that large positive signal during swing phase. And so it's reliably identified, and it presents a consistent step segmentation. I should say that, I won't claim that it's exactly foot contact, but so insofar as it is a consistent step segmentation is what was important for our purposes, and that it captured the lengthening phase, like I said.
Next question is from Natalia Franco Montegodu. You mentioned in the beginning this injury is described as an overloading injury. How do the results relate to that classification? Is it accurate enough to call it overloading?
Yeah, so strain injuries happen when tissue is presented with a failure strain. And so circumstances that make the presentation of a failure strain more likely would be considered perhaps high risk circumstances. So that's long links being stretched very fast and under high loads. We quantified the first two of those. The last one would be a kinetic analysis, which, like I said, we didn't do, but it should be done in future work. And so I hope that answers the question. Overloading, yeah, insofar as long lengths and great lengthening velocities relate to high loads, then I think it's relevant for that purpose.
Next question is from Kristen Stoodle. For the peak MTU length versus running speed plot, do the points where the peak MTU length was close to 1.15 corresponding to subjects with shorter resting or upright stance MTU length?
I'm not sure. I'm not sure. We could look and see if there's an effect of stature, perhaps.
Let's see. Oh, I didn't. Okay. The next question is from David Hosman. What is the benefit of normalizing MTU length to the neutral hamstring lengths during static calibration compared to normalizing to leg length? And would this be useful in patient groups where static trials are sometimes performed with knee flexion because of the disorder? So, related question.
Mhm. So in the model, as long as you have a model of the lengths of each segment, even if you don't have a standing trial, as long as you have a model that's calibrated based on the lengths of the different segments, you could still pose the model in a neutral pose and get the neutral length. I think, as far as your question, normalizing by neutral length versus leg length, they're probably correlated. People with longer legs probably have longer hamstrings. But I think it's just more interpretable. Yeah, I think that it's, just a useful reference. And the reason why it's important to normalize is because if you don't, then you'll have this large offset. There'll be a lot of variation in the peak length of data that is due to stature and not due to running condition or running speed.
Next question is from Christy Godoy. Uh, Thank you very much for sharing this work. I apologize if this is a basic question, but I'm curious about how you scaled your model. For this study, I assume the segment length is important in relation to muscle length. How did you verify this change in length is more or less what was expected?
So this is a part of a standard procedure in musculoskeletal modeling. In OpenCap, one of the first steps that you do is you have the person stand in an upright posture. It identifies, for example, the knee joint center, the ankle joint center, and the hip joint center. And so you'll have a sense for how long the femur is, how long the tibia is. And this is used to scale a generic model. The generic model in OpenSim will specify where the hamstring attaches to the pelvis and to the tibia for a particular person with a particular height. But to scale that model up to different people, we use the information about the relative lengths of the segments, tibia and femur, for example, and it does it for all the segments. And so it will adjust the geometry of the hamstrings based on the stature of the person.
Next question is from Sylvia Cabral. In this type of or in these types of tasks, the participants start quite far away from the camera and look small in the camera view. Did you experience any problems with the model due to this, or in your
Yeah, I
results?
don't I don't think that there were any problems because of that distance. Like I said, sometimes the reconstruction would fail. Sometimes, we did this on a public track, and so other people would be running, and we couldn't just tell them to stop running. Sometimes other people would appear in the capture volume that we didn't see, and so it was for reasons like that that sometimes the kinematic reconstruction would fail. But I don't think we had any issues necessarily with the distance. We wanted a longer distance because we wanted people, especially for the accelerative running trials, to get up to that constant speed. And we were using this metronome method to try and match the speed roughly. And so we wanted them to have a decent distance to run to kind of get used to that speed before they then accelerated.
Yeah, and I assume you played around with that capture
We
volume.
did, yeah. We tested many times, yeah.
Yeah. Next question, and it's kind of similar vein of just like using OpenCap. It's from Peter Vandenberg. Would you mind commenting on any encountered challenges in the OpenCap setup and processing? Do you think the use of two cameras may have led to the outliers in your discarded data, or were there other factors?
Um, So we actually did 2 and 3, and we found that 3 would actually, or sorry, 2 would synchronize better. So we ended up going with 2. I think in the original OpenCap publication, it was no less accurate for 2 cameras than 3, if I remember correctly. Um, a lot of this, especially for running, has to do with sometimes you get errors where the foot may go missing. And so, where do you put that third camera? If you put it more in a frontal plane view, then when the foot goes behind the knee, it kind of disappears and you can't see it. But the 2 cameras on the side can. And so they'll provide a more, reliable estimate of tracking, especially the ankle joint center, which can be obstructed by the knee with a frontal plane camera. Yeah, that's one of the
Yeah,
biggest
so
challenges. Yeah,
mostly like occlusions were things that
right. And
would
because it's
cause.
primarily, a sagittal plane activity, having those 2 cameras that capture the sagittal perspective on either side was sufficient.
Yeah. Uh, The next question is from Gio Richards. Well, yeah, could you mention to what caused the simulation failures you mentioned? You've covered a few of them, I guess.
Yeah. I honestly don't know. If you've ever worked with OpenCap, sometimes you do a trial and it won't even appear, and it can happen for different reasons. I'm not even sure. That would be a question for the developers. But it's obvious when it happens.
Yeah. Next question is from Alessandro Pellegrini. Thank you for your insightful presentation. They're also looking at overstretched injury mechanisms of hamstrings in football players. And these injuries tend to occur at relatively low speeds, but with high muscle lengthening, like you've suggested. And the literature suggests that such movements primarily affect the medial hamstrings, particularly at the proximal free tendon portion. Has a few questions tied to that. Which musculoskeletal model did you use? It sounds like you used the OpenCap one out of the box, but and then
Yep.
what was the standing posture you used? You've covered that a little bit for the static acquisition, and then do you also have data for the medial hamstrings as well as the gluteus or erector spinning?
Yeah, I remember the first and the last, so you'll have to fill me in for the intermediate ones. For the first question, it was Lie Arnold. It was the default OpenCap model. So Lie Arnold, and I think it has Scott Aldrich's adjustments to some of the muscles, their geometry with the that affect the hip moment arms. Regarding now, I forgot the last question.
No, that's all right. Do you have data on the medial hamstrings? So
Yes, yeah, it's all there. We did biceps femoris just because in some of Daryl Thelon's work, that one peaks the most. They have a similar pattern, but it's stretched the most and has the largest stretch rates.
Sure. I guess gluteus you would have as well.
Yeah, we would
Erector
have
spinae.
we would have gluteus. I don't know that the kinematics, this being a kinematic level study, would be super relevant. You could imagine that the muscle activity, force production of the glutes would matter insofar as they are turned on. They're going to reduce the need for hamstrings to turn on to extend the hip. So you'll
Yeah,
have implications there. So maybe that would become more relevant in a kinetic analysis.
yeah, for sure. And the middle one was about the standing posture for static acquisition, which you've already covered. I think it may have been asked before you were talking about that, so I'll have to rehash that. So the next question is from Karen Walker. Awesome presentation. Thanks, Reed and team. Given what you have found, do you have any ideas for running gait modifications that people should adapt while accelerating for the first few steps of running to avoid the hamstring injury? The contributions of knee flexion and thigh rotation were interesting, so curious if you had any thoughts.
Yeah, I want to be really clear that, you know, to hesitate and say this was not a prospective study. We have ideas about this, that whole slide where I talked about, the hip and the knee flexing together in early swing and extending it together in late swing. That needs to be tested in a prospective design to see if it is predictive. There have been some prospective studies that have been done to look at kinematic risk factors for hamstring injury, but very small sample sizes have been the case. And so I'm excited about the use of OpenCap to do large amounts of movement data, collect movement data across a large sample, to have a better powered prospective research design to get exactly at this. Like, what should we look at? We have ideas, but they need to be tested.
Next question is from Evan Block. First and foremost, thank you for the informative presentation. You briefly mentioned the potential application for wearable GPS units as a way of measuring running speeds and hamstring length. And just wondering if you could talk a little bit more about that idea and as well as mention any other types of inertial or IMU techniques you came across in
Yeah.
literature.
So I think a lot of, it's becoming more and more common for teams to use GPS units worn on some sort of, elastic vest, for example, to track running speed and things like this. And I know I've spoken with some sports scientists with teams who, for example, will use exposure to running speed to sort of gauge to program the load for the following week. They use it as a gauge for, how taxed are our athletes, how often were they sprinting and things like this. And all that I was suggesting is that, if you use the logic that running fast results in larger hamstring lengths, then maybe high running speeds are an appropriate surrogate. for monitoring an athlete that you think may be at risk for hamstring injury. All I was saying is that maybe we should also consider the accelerative nature, because our data suggests that the hamstring length can be equally high, even if the running speed by itself doesn't indicate that. So now regarding IMUs, I love the idea of a shank-worn IMU. So with soccer players, there's instrumented shin guards. It's not too difficult to imagine clipping a thing onto the side of the foot. And, if you're familiar with the load monitoring space, it seems like what seems to be a good idea is to have metrics that are injury specific, joint specific. And, the shank will tell you a lot about what the knee is doing. And so quantifying the motion of the shank would probably, I anticipate, would do better than some sort of global thing like a chest worn unit. So yeah, I'm excited about those opportunities.
Sure. Next question is from John Pope. What are your initial suspicions on the hamstring's role in deceleration from your preliminary data, and stabilizing force during braking force attenuation is a possibility?
Right. So you imagine that the forces during deceleration are going to be largest in the extension action of the knee when it hits the ground, right? That's when you have braking ground reaction forces, which are going to require large knee extension forces when the foot hits the ground. But I'm not sure. I mean, this is why we're interested in testing it. When you decelerate, I have a football background and I'm familiar with how wide receivers are taught, for example, to decelerate and go into a cut, and they're taught to sink their hips, and you lean forward like this. And I mean, that's going to stretch the hamstrings when the pelvis rotates forward. And if you're placing your feet further out in order to orient the ground reaction force, in a way that you would like to actually slow down the center of mass, now you've got a foot that is placed more forwardly, a more anteriorly tilted pelvis. And that's kind of why we're seeing, like, even though they're not running as fast, the hamstrings are still stretched relatively large. I'm not sure what the loads are, and I hesitate to speculate, but I'm really interested to dig into that further.
Yeah, for sure. I guess an add-on, they have one more question, is, do you think there's anything potentially about like quad versus hamstring imbalance in strength?
I'm not sure. I feel like somebody's looked at that with injury risk factors or maybe predicting return to play. Those studies, they seem to be, well, yeah, I'm not sure.
Great. I think we'll go ahead and wrap here. And so thanks again, Reed, for a great talk and sharing your research. And then thank you for all the questions that have come in. Please be sure to click on the link that will appear at the conclusion of the webinar and take our survey. That'll help us improve the webinar series and choose upcoming topics. This webinar series is supported by 2 grants from the NIH, including the grants that support our Mobilize Center and Restore Center. We're grateful for the support, which allows us to run these webinars and other events. And just want to thank everyone for participating. We hope you'll continue to stay involved with our centers, and that we will see you in a future webinar. Have a great day.